For decades, a single rule defined every smartphone ever made: the screen had to stay flat. Traditional glass and circuits are rigid. Bending them even slightly causes them to fail instantly. But designers had long imagined devices that behaved more like paper. They envisioned newspapers that could roll into a pocket and tablets that folded like wallets. Realizing that dream required a shift across multiple fields simultaneously. Breakthroughs in chemistry were required before mechanical engineers could begin work on the complex hinges, while robotic specialists developed precision to assemble them at scale. It became clear that incremental improvements to existing screens wouldn't work. The hardware had to be reimagined from the substrate level up. This challenge triggered a decade of research, involving billions of dollars in R&D, and a global race to bring a viable, flexible display to the consumer market. Look at the layers inside a standard display. Because each rigid component expands differently under pressure, bending causes them to delaminate and crack. The solution was replacing the rigid foundation with a flexible plastic substrate, allowing the OLED to flex in unison without separating. While this solved the internal breakage, the plastic surface felt soft and scratched easily. Consumers expected the durability and premium feel of traditional glass. The response was ultra-thin glass, a material specifically engineered to possess the clarity of glass with the flexibility of a polymer. This glass is polished until it's thinner than a human hair, then chemically strengthened and layered with shock-absorbing films to handle mechanical stress. However, solving the material problem only moved the stress to the mechanism doing the folding. Even with flexible glass, the most critical part of the device isn't the screen itself, it's the mechanical hinge hidden beneath it. The physics of folding are unforgiving. Too much pressure crushes the OLED. Too little creates a permanent crease. To manage this, engineers developed hinges that guide the display into a wider teardrop shape inside the housing, significantly reducing pressure on the glass. Building these mechanisms at scale requires a level of environmental control usually reserved for semiconductor labs. Robotic arms assemble components measured in microns, while laser cutters and AI inspectors ensure that not a single speck of dust is trapped between the folding layers. The finished devices are then put through stress tests involving hundreds of thousands of rapid cycles and extreme temperature shifts. A modern foldable is a mechanical enclosure built specifically to protect its own fragile components from the basic laws of physics. Today, these devices are mass-produced items, hiding the years of research and investment required to make a screen fold. The industry is now expanding into trifold designs, compact iterations, and new software layouts designed for larger, flexible canvases. Current research is focused on rollable displays, stretchable electronics, and materials that may eventually remove the visible crease altogether. This isn't just about making a phone faster. It is about changing how we physically interact with computer hardware. Foldable screens demonstrate that even physical limitations can be overcome by questioning why a screen needs to stay flat in the first place.